shall conclude a discussion on radiative effects. Well, I'll start and conclude the discussion on radiative effects on the MSSM Higgs masses. So the story up to now is that it was very easy to write down the 3-level Higgs potential with all the free parameters it had, and then minimize it and get out 8 in principle Higgs, because 2 complex doublets, and then 3 of these 8 were Goldstone modes, which were absorbed by the W plus minus and Z, leaving 5. 5 out of these 5 physical Higgs, 2 were charged and 3 were neutral. Out of the 3 neutral, 2 were CP even and 1 was CP odd. So there was a nice spectrum of these 5 neutral Higgs, and we saw that under most standard scenarios their masses were ordered, and the neutral Higgs were called H, H, A and H plus minus. And just to remind you where they came from, here there is no ambiguity. H plus minus are complex conjugate pair which come from the original Higgs, H1 plus minus and H2 plus minus. These are altogether 4 real modes, but 2 of them are Goldstone and the other 2 are these. These 2 come from the real parts of H1 neutral and H2 neutral, and this guy comes from the real part, from the imaginary part of H1 0 and H2 0. Again, this is 2 modes, this is just 1, so the other one is a Goldstone. So this was the structure of 5 neutral Higgs, and we found various mass relations among them, and one of the striking mass relations was that the Higgs small h has a mass less than the minimum of the Higgs A and the Z boson, which has a mass around 91 GeV. Okay, which means in particular, since this is a stronger bond, that is the minimum of these 2, so even in case Ma is very heavy, MH has to be lighter than the Z boson. Okay. But this isn't a very favored scenario because it would require 1 Higgs at less than 91 GeV, which is not quite consistent with the experiment. Although as we'll see, it's not quite inconsistent either, it's somewhere on the borderline. And it depends, as usual, what's consistent depends on what you assume. But in any case, this is a 3-level relation. And the crucial point here is that 3-level relations among Higgs masses, but are particularly influenced, strongly influenced by loop corrections. And we'll see that the influence can be as much as 50%, which means that instead of an upper bound of 91 GeV, it could go up to as high as 135, okay, by taking into account loop corrections. Now for loop corrections, of course we are going to do 1 loop only. So the only object we are interested in here is the 1 loop effective potential, and I mentioned last time, I think that's where I stopped last time, that the 1 loop effective potential has a sort of universal form. I write it as delta V of 1, and it's equal to 1 over 64 pi square, the super trace of m to the 4th log m squared over q squared minus 3 by 2, where these are the scalars that couple to the Higgs. Sorry, these are all the particles that couple to the Higgs. So m squared is for bosons. M squared has 2 possibilities. It's either m for some boson, the mass square matrix, which is a matrix which is n by n, where there are n bosons in the theory, whatever that number, and it can also be the square of the mass matrix for fermions. And the point is that you sum this over all bosons that couple to the Higgs with a plus sign, and then minus with a minus sign over all fermions that couple to the Higgs. And the way you are supposed to think of it is that there is a loop, basically internal loop of these particles or these particles, and Higgs, all possible combination of Higgs attaching by such vertices, and such vertices are H psi or H phi phi. Okay, and you sum over all possible ways of attaching them, and that's when you get this Coleman-Weinberg type. Popular, the derivation is in field theory textbooks, so I'm not doing it here. And this is just one way of studying loop corrections, wherein you say that we consider the effective potential with all possible numbers of external legs, sum over everything, get this correction, then we add this correction to the tree level Higgs potential, and we minimize the whole thing instead of minimizing just the tree level potential, and we see what corrections we get. Yes.
And then in the surface
Yes. So that's the point which I also should have said, and I mentioned it last time. Because this is a super trace, and because the mass squared matrices are strictly degenerate in the limit of supersymmetry, if all the supersymmetry breaking soft terms are turned off, then this thing is zero. Okay? That means that the important corrections to the Higgs potential are generated by Susy breaking terms, at least in one. Good. Now, this is a rather complicated thing to evaluate because you can really have everything possible circulating in this loop. But there's a simplifying assumption, which is to note that these are Yukawa couplings. So, for example, if this was a fermion loop, then this is an H psi left, psi right type of coupling. But Yukawa couplings are particularly large when the fermion in question is the top quark. Okay. So, we could make a simplifying assumption that we calculate this running over only a subset of the possible particles in the loop. So we make this assumption. We restrict only to the top quark as well as the stop, its fermion partner running in the loop. And that's because top Yukawa coupling is largest. However, it's important also to keep in mind that there are independent Yukawa couplings for top and bottom, because one uses the Higgs H1 and the other uses H2. And the wave of H2 and the wave of H1, that ratio is tan beta, V2 over V1. And depending on the value of tan beta, it could be that even the bottom Yukawa coupling is comparably large. Okay, so we make assumptions that that's not the case, and then all these assumptions can be corrected. In principle, after all, this is a well-defined quantity, and you can sum it up over everything in the standard model with no assumptions. But that's not how one normally does phenomenology. It's better to start by computing the leading corrections, see how it's going, and then add all the other corrections and estimate them as you keep adding them in, and see if they're important or not. So what we'll be doing for almost all this lecture, I think, is to just consider the top and the stop. Okay, now that's great, because of course, as I told you already, if I really considered all fermions, then I would have all three generations of fermions, as well as I would have the left and right fermions mixing, so I would have a huge 6x6 mass matrix to put in this formula, which is horrible. But if I restrict to the top, then I only have to worry about 2x2 mass matrix for the stop. For the top, it's just one thing, and for the stop, there's the left and the right stop. Okay? Okay. Now, so this is one comment. The next comment is that for the stop contribution, but I wrote it long ago in this course in the context of tau lepton of the stau. And the stau and the stop are very similar as far as these things are concerned. But I think I better write this matrix now because it will be helpful to keep in mind what ingredients it contains. And when I discussed fermion mixing, I had actually spent a little time on this third generation assumption, which was that only the third generation, that flavor mixing is small, but left-right mixing is large in the third generation, in which case we can forget the third generation mixing with the first and second. So, for the stop, it was something like, this is M stop left square. This is a SUSY breaking parameter, and it's actually the same because the left-handed guys are doublets of SU2. This is really the third generation lepton, third generation left mass square soft parameter. In the other place, there will be the corresponding right, which is independent. This is a singlet only for the right stop. This is for the left stop and the left spotter, I suppose. Okay. Then there is some term that depends on mz square, which is a term that we are going to neglect. This comes from D terms. You can guess that mz squared comes from D terms because mz, the mass of the z, has coefficients which are gauge couplings, G2 and Gy, and things that depend on gauge couplings in a potential come from D terms. Okay, that's the whole point of D terms, that they come, they arise because of the gauge coupling. There's some supersymmetric combination of gauge couplings. So there's a similar term here. I'm not writing it precisely because it has some factors of 1/3 and so on, which I don't quite remember. And then the last term in this is the mass of the top quark itself. That's the same here and here. Okay. The thing to keep in mind is the mass of the top quark is the same thing that would be the mass of the stop quark in the limit of exact supersymmetry. Okay, so it must appear, and it must appear diagonally. And then if you add soft SUSY breaking terms, then you have these two extra contributions. So you should not confuse that these are the mass of the stop left, the left and right stop. They are just the extra piece in that mass coming from soft SUSY breaking terms, which need to be added to these two pieces. Okay. Then the off diagonal term has a mass of the top again times this A. If you remember, A was also a soft SUSY breaking term, and then there was this mu tan beta. Mu is part of the Higgs superpotential, and here there is the same thing with some complex conjugations. So this is the matrix. This we are going to neglect. And this is the matrix that we are interested in if we want to evaluate stop contributions to this effective potential. Now there are two levels of doing this calculation. The first level is to make another simplifying assumption, which is, so this is a whole series of assumptions, and then we will be relaxing each of them and seeing how it goes. So the simplifying, so we've already simplified by restricting to tops and stops. The next assumption will be to neglect these off-diagonal terms, okay? Which is sort of right away a bad assumption because remember MT is the thing that's large, okay? But you could rig it up by making mu and AT small. These are in your hands. Okay, mu is the mu parameter which couples H1 dot H2, but you could take that 0. And AT is a soft parameter, you could take that 0 as well. Okay. So you could avoid these off-diagonal terms. So we would say that this is the assumption: no T tilde left, T tilde right mixing. Okay. And along with that, we might as well also simplify by saying that the soft parameter for T tilde left and right is just the same. And we'll call it M T tilde square. A warning in case you are going to check, you are going to compare this with the Trace Roy book. They somewhat, unfortunately, switch notations so that what they call M tilde square or something is the full stock mass, not just the soft breaking part of it. So this plus that is their M tilde square. But I'll just stick to the fact that this notation denotes soft masses. Okay. So with that now we can proceed. And now we have that so the stop, we don't have a notation for the stop mass anymore because we've already used M T tilde for the soft breaking parameter, but I won't need it. I'll just write that the stock mass square is equal to this soft parameter M T tilde square plus M T square. Okay, but let's also remember that MT, how did the mass of the top originate in the first place? It came from a Yukawa coupling FT, which coupled the Higgs to the top, and then the Higgs itself, which is the one that's going to get a wave, and that's H20. Okay, so take the wave of H20, that's real, and multiply by this, and of course that wave we've given a name. This is V2 by square root of 2. Okay, but in this process, you see that it's not just that the mass is the Yukawa coupling times the wave, but you can also see that so this I forgot to say now, but I said it last time I think. The mass matrix over which we want to evaluate that super trace is not really the mass matrix after the Higgs has a wave, but is the mass matrix before the Higgs has a wave. Okay, it's what people call the field dependent mass matrix, and the reason is we are looking for a Higgs potential. Okay, so to find the Higgs potential, the quantity m squared in that Coleman-Weinberg formula is actually the quantity where the Higgs appears. So this combination Ft times the Higgs appears wherever there should be a mass. Okay, so when we are going to evaluate the effective potential, then this is what is called the field dependent mass. It's just a coupling which, as soon as the Higgs gets a wave, becomes a mass. But of course, besides the wave, there's another term where the Higgs is actually a field because we're shifting it by its wave, and that also multiplies Ft. Okay, so this is like a field dependent mass. This is just a constant mass, and it's the field dependent mass that goes into the formula. So what we have to do then is to calculate that m to the 4th log m squared term that I wrote for you earlier, plugging in all these things. And now I'm going to erase this mass matrix, but I just want you to remember that we've dropped these terms, and at the end of this lecture we'll bring them back. So these are the terms that we'll bring back when we relax the assumption of no T left, T right mixing, and we actually add in the effect of that mixing. That's when we'll put these terms back. So I won't be writing that. Okay, so under all these assumptions, that formula becomes delta V due to contributions of the top and the stop. This is what this notation means. Is going to be 3 by 16 pi square. I think I originally had 3 by 64 pi square, which is the field theory computation. And then you're supposed to notice that there are 4 guys contributing among bosons and 4 among fermions. I cannot anymore find here it is. Yeah, 1 by 64 pi square. Good. So what's this 3 coming from? Colors. Yeah, it sounds like Thank you. I think that's correct. So there's a 3 as well as a 4. This should have been 1 by 64 pi square. The 3 is the colors, and 4 is the fact that we have that the stop is complex and we have 2 stops, the left and the right stop. On the fermion side, there will again be a 4, obviously, because in supersymmetric the number of degrees of freedom match even after the Suzy breaking. But this time it will be the doublets, the left-handed top doublet and the right-handed top singlet. So anyway, it will be 4 again. And so the answer is 3 by 16 pi square times, just copy wholesale what we wrote earlier. So here I am putting this quantity, mt tilde square plus mt square, where mt is that. Sorry, where mt is not that, mt is actually that. Sorry, someone should have stopped me. The whole point of it being field dependent mass is that this is the field and not its width. Okay, so mt tilde square plus ft squared h20 mod squared. So that's the m to the 4th in the original formula, and then a log of the same matrix mt squared. It's not a matrix anymore, it's just a number, because we assume that matrix was diagonal. So this is the stop contribution, m to the 4th log m squared over q squared minus 3/2. Okay, and now we have to subtract from it the top contribution, but that's very easy. It's exactly this with mt tilde not there, because that's the only extra thing in the stop mass. So you just have to subtract whatever was there before without mt. Okay. That's it. And you can see very manifestly that turning off the soft Suzy breaking mass term makes this 0, which is exactly what we expected. Okay, so this is the new potential. So the way to understand this is that the original potential was whatever I wrote in the last lecture, and it depended on the various Higgs. Okay, and it just came from the Higgs potential, which was just some quartic term and some quadratic term. And I listed all the various contributions. Some of it comes from the supersymmetric part, some comes from soft breaking terms. Actually, nothing comes from soft breaking terms in the Higgs potential, because soft means dimension 3 or less. So mass terms do come, but the quartic term doesn't. Okay, and so I listed all that, and to all that you have to then add this. Okay, now the special thing you see when you stare at this is that it only depends on H20, which means only on the second Higgs doublet and the mutual part of it, not on the first Higgs doublet. Why is that? It's just because the top quark gets its mass from the second Higgs in the MSS. Therefore it doesn't couple to the first Higgs at all. Okay. So now we have to minimize this. Minimize V plus delta V. Okay, but let's recall that when we just minimized V alone earlier, we had got some 3-level relations among various parameters to start with, and those relations will change. So actually we had done 2 different things. First we minimized the potential, put in the waves, and got 3-level relations among the parameters. Secondly, we differentiated the potential to second order in the Higgs to get the Higgs mass matrix. Okay, and then we expressed that mass matrix in terms of various parameters. So there were 2 steps. But the first step led to these relations, which you'll find in your notes. Relations for m1 squared and m2 squared plus mu squared. Where m1 squared and m2 squared were the soft Higgs masses. Okay. And the first relation was that this is V mu V2 over V1. The second relation is just the same with 1 and 2 interchanged. And then some stuff like this, which ultimately can be traded for some W or Z mass. And the same same thing, give it the opposite sign because of the 1 2 interchange. So these were the original relations, and now what happens is that they'll change because of this new term delta V, but there will be a few simplifications. Yeah, the first simplification, of course, is that this does not change. That is immediate. What was this? This was obtained by minimizing in H1. H1 doesn't appear in this correction, so this relation doesn't change. This relation was obtained by minimizing in H2, and H2 does appear here. So in particular, this 1 to 2 symmetry is now broken. Okay, because we favored the top quark out of between the top and bottom doublet, we favored the top quark, so the 1 to 2 symmetry is broken. Of course, it's broken in real life because the top quark and bottom quark masses are not the same. Okay. So this relation changes, and in fact it changes to, or maybe it's best if I write how much it changes by. So I'll write another term on the right hand side here which needs to be added. All the rest will be as I've written it here. So it changes by an amount minus 3 by 16 pi square ft squared. Remember, the thing that changes this is you're supposed to differentiate. So this original relation came by differentiating in H20 star and then dropping an overall factor of H20. Okay, so now we'll do the same here. So we differentiate in H20 star and then it will pull out a factor of H20 because H20 always occurs in the form of mod square, and we'll drop that. And so that's how you get out this Ft square. There must be a 2 also, but I think there might have been a 2 that was dropped in there. Or maybe I think there's a 2 coming up right now. This 2. And after we differentiate it once, then we can set everybody to their wave values. So from now on, H20 is set to P2 whole square root of 2. So you get this form log of the same thing. Minus 1. That happens because when I differentiate in all possible ways, then I get 2 different contributions and finally get to minus 1. And of course, I think this bracket isn't needed. And of course, I expect one more contribution, which is the same as this with mt tilde squared dropped. So mt squared log of mt squared over q squared minus 1. So that's the extra term in this second relation. Okay. Another observation, of course, which is pretty obvious, is that we needn't look at the charged Higgs because the charged Higgs also don't appear here. Okay. So the only mass matrices we need. So now we've done this. We want to look at the mass matrices, and remember there were 2 by 2 mass matrices for neutral Higgs where this will appear. Those are the mass matrices for real H10 and real H20, and the other one was imaginary H10 and imaginary H20. In both of these, some contribution from here will appear. But again, as we'll see, there's a nice simplification. So let's start with the mass matrix obtained by differentiating the full potential V, I call it V plus delta V, in the imaginary part. Hi0, Hj0. This I and j go over 1 and 2. So this is going to be a 2 by 2 matrix. If delta V was not there, it's a 2 by 2 matrix I've already written for you. And delta V is going to change that matrix. But in fact, the change will be restricted, and that's very easy to see. In fact, del by delta V by delta in of H20 is the only non-zero piece, non-zero correction. That's pretty obvious, because when we differentiate in im hi0, hj0, if I and j are 1 and 1, of course nothing comes from here. If any of them is 1, nothing comes from here. So both of them have to be 2's, and then we get a correction. So that means in terms of the 2 by 2 structure of the original mass matrix for this particular pair of Higgs, the bottom right component of that matrix gets a neutron. Okay, so I'm not going to write down what is this quantity, del of delta V by image to 0. Image to 0, it's another derivative over what we did here. It's very easy to calculate. And you get something logarithmic. However, the interesting part, okay, so maybe I have to write it. Now I'm writing the total contribution from the tree level V as well as this correction, and the total contribution comes out to be what it was from at tree level, which was m2 squared plus mu squared minus this quantity over 8 v1 squared minus v2 squared plus 3 by 16 pi squared ft squared. If I've just forgotten what I already did and I'm doing it again, it's a different calculation. This one was obtained by differentiating the potential once, okay, and then dropping an H20. This one is obtained by differentiating the potential twice. Okay. Now, why are they the same? They seem to be the same in the sense that the relation we got between parameters was corrected by this, but the change in the effective potential is the entire right side of that relation, and therefore it's exactly what it was even without this extra term, namely b mu v1 by v2. Sorry, black bracket must be wrong. Both brackets are wrong. Right. See, you have to think what's happening here a little bit. After you differentiate V the first time, you get out a factor of H20. Okay, because you're differentiating in im H20, but H20 always comes with its own square. So you get one factor of H20 outside. Okay, but that factor doesn't get a wave because it's im. If it was real of H20, it could have got a wave. Since it doesn't get a wave, the next time we differentiate, we have to differentiate that outside factor. We can't differentiate an inside factor because then it will go to 0. Okay? That's why this term, which you get after second derivative, is the same as this term you get after first derivative and dropping an H20. Okay? And it's a speciality of the imaginary Higgs part. It won't be true in the real Higgs when we do the real Higgs mass matrix. Okay? So therefore, the correction in the mass matrix is the same amount as the correction in the equation which said that this is equal to that at tree level plus this, and therefore when expressed in terms of the soft breaking parameter B, there is no change in the mass matrix. This is the key point. Okay. Therefore, when expressed in terms of B, or B mu, there is no change in the im H10, im H20 mass matrix. The top left and and top right and bottom left entries anyway trivially didn't change because they involve H10. The bottom right could have changed, and in fact it changed. Okay, but the change was exactly by an amount such that that plus these values adds back to this. Okay, so when we say it doesn't change, we mean it doesn't change in terms of this parameter. It does change in terms of these parameters. So it depends on what parameters you describe it in terms of. But obviously this is very convenient. And what it basically means is that under this assumption of no left-right stop mixing, we can forget about all the Higgs except the ones which come from the mass matrix involving real components. Which are the components that we have? This is all we need to consider. Okay. In turn, this will have no change when I and j are 1, 1 or 1, 2 or 2, 1. So the only one operative one is 2, 2. And this eventually comes out to be 3/4 ft squared mt squared log mt tilde squared plus mt squared. So this is a calculation you can do. Yeah. No, sorry. This is not, no, this is only delta V. Okay. Because V of course has all four components when I differentiated H, I0, Hj0 real parts. But delta V has only the two components, so it only adds something in the bottom right of the matrix, and my claim is that's the thing it adds. Okay. Now we can massage this expression slightly using the fact that this is an important expression, by the way, so we'll keep using this. We'll just rewrite it to highlight the dependence on the angle beta. So for that, we again recall that mt is equal to ft times v2 over square root of 2. Okay, the relation between mass of the top and Yukawa of the top in terms of the Higgs wave. Okay, now we can that this enables us to solve for ft as root 2 by v2 mt, and the next thing we can do is write this as root 2 mt into square root of v1 squared plus v2 squared over v2 1 by square root of v1 squared plus v2 squared. So I've just introduced these two factors. Okay, but now the first factor, square root of v1 squared plus v2 squared over v2, this is the reciprocal of sine beta, because sine beta is v2 over that, cos beta is v1 over that, and tan beta is v2 over v1. So this has a sine beta downstairs, and this last thing is related to the Fermi constant Gf. Okay, because remember the Fermi constant is basically it's a quantity of dimension 1 by energy squared, and it goes like 1 over the wave squared. So this actually goes like the Fermi constant Gf, but there's a square root of 2 which I always find confusing. So this actually goes like square root of Gf, but Gf goes like 1 over v squared. So this is actually square root of, but for conventional reasons, square root of 2Gf. No, square root of 2. Yeah, unfortunately that's so. Square root of 2Gf is 1 over v squared. Just a fact. Okay. Very good. So therefore, this is all fine, and we can use this relation to eliminate ft squared from up here. We just square this relation and put it in there. And so this implies that the correction term derivative of delta v with respect to h2 real h20 real h20 is now 3 by root 2 pi squared GF mt to the fourth upon sine square beta log, the log hasn't changed. We just got rid of FT in terms of known quantities. It's just to highlight what the known quantities are. So GF is 1 over something like 256 or 276 GeV squared. I've lost that here, but I had probably said it at some point. Okay, so the important point is this is a known quantity. Mass of the top is a known quantity. It's about 175 GeV. Okay, so the only unknown, okay, so sine beta is of course unknown. And the top breaking term for the stop is unknown. But notice that the dependence is very slow. This is like a log. So we can pretty much estimate it by just putting mt tilde into the TeV range. And it won't matter very much whether it's 1 TeV or 5 TeV. So this is an important, this is some famous quartic correction. So we have to focus on this particular formula a little bit. So the first thing I'll do is to rewrite this as epsilon h upon sine square beta, where everything on the right side that's not sine square beta is called epsilon h. So it's defined to be 3 by root 2 pi square GF mt to the fourth over, no, not over anything, log of, so here this ratio is 1 and plus mt tilde squared upon mt squared. Alright. Now if mt tilde is a few TeV and this we know is 175 GeV, then that's just like a factor of 6 or something. Squared comes to 36. Okay, so somewhere between 36 and maybe you could accommodate another, between 36 and 100 or 150. So log of that is somewhere between 4 and 7. Okay, so the range of this is around 4 to 7. This stuff we can calculate out, and I'm proud to say I actually did it today. And at the end of that, you find that it comes out. I did it, but I have a feeling I didn't write down what I got. Very bad practice when you're a phenomenologist. Yeah. And of course, yeah, so that's right. So this comes to about 110 GeV. Gosh. I should have got some more notes from my office, but I got something like that the whole thing, by the way, dimensionally this is energy squared or mass squared, because this is mass to the -2 and here the mass to the fourth. And so I finally got something like very annoying, 1 by 256 or 260 GeV squared. Yeah, GeV squared. This is 175 GeV to the fourth. And I just wish I had written this down, and I'm not able to remember it, but I think it's about 100, the whole thing is about 110 GeV square or 100 GeV square. I thought I was sure I had written it, in fact. Maybe I'll need it later, so I'll bring it up when I need it. Anyway, it's all before your eyes, you can do it as well. And of course, if you want to minimize this correction value, then you can take beta to be as large as possible, namely pi by 2, in which case the denominator is 1. Okay, this is a number. in GeV square, and I don't remember what it is. But it's something like 100. And we could perhaps try an online calculation. This is better to write with a 2 here and a root 2 here because it's actually root 2 GF. So this first number is 1 by 6. That effectively cancels this number, which will take to be 6. This one will take to be 1 by 260 GV, that's in GV squared, and this number is 175 to the 4th. And now we just have to do it. So we can forget this. 260 square, is it?
No, GV square.
I think
no, GF is square.
GF is, that's 260 square. In fact, I remember squaring because it's root GF, that's 1 by 260 GV. Okay, so good. So now you have it all in front of your eyes.
Around half.
I think it comes to about 120. That's as good as I'm expected to try and do now. Okay.
Yeah, 170.
Alright. Good. Okay. So what was the purpose of doing this? This is a 2 component of a mass matrix, and we've just found an estimate of epsilon h. The point I was trying to stress is that epsilon h is not something you can play with very much. There are in fact no free parameters in it except mt tilde, which is a soft breaking parameter and therefore free, but it hardly matters because the best you can do is taking it to be 1 TeV or 5 TeV. That about changes this only by so much. So there's not much you can change, so it's like a number around 120 GV squared. Of course the denominator can do a lot. It can blow this thing up to infinity if beta 0, or the denominator can be 1, that's its maximum value if beta is pi by 2. Okay, so with that we can now write the full mass matrix. So now after all this stuff we'll finally start to get some physical answers out. So the full mass matrix now is, so everything I'm writing here was written before when we did the tree level calculation. And it's only in the bottom right component that something extra will show up. I hope you remember that we use the known value mz as a parameter and the unknown value ma, but this nicely parameterizes all the other x's in terms of ma. And ma is something that we often take large, that's called the decoupling limit, which is reached when ma is about 300 GeV, and then we get somewhat robust bounds by all the other x's. A stands for the axial vector or CP or x. Okay, I'm sorry, somebody's trying to call me for the third time. So this had these, so this is just this I've already written down exactly this form, but now the new term is in this place and it's epsilon h over sine squared. So I hope that's it. After this long song and dance, the only change in this mass matrix is this piece over here. Okay, therefore now we can write down the eigenvalues, which is a straightforward exercise, and the eigenvalues are going to be called the Higgs's small h and capital H. These are the CP even neutral Higgs's, and if you remember, it's small h which is somehow the lightest Higgs most of the time, just about in all scenarios. This is the one which was bounded above entry level by min of ma and mz, and now it will be bounded by something a little larger than that in In fact, if you don't really want to go through the gory details, well, there are no gory details, that is like this. So here is one place where epsilon appears, and then there is a square root. So again you see where epsilon h appears, it appears here, and without it, that we have back to the old formula for the masses of small h and capital H. Slightly in a different notation, because here I have sine square of 2 beta. No, I have here sine square of 2 beta, and here I have cos square of 2 beta, where it is inside this bracket and it's squared. So that's how it is. Okay. So this is one change. Now let's find out all the other relevant changes because of this epsilon h contribution. The angle by which you need to rotate this basis to get this basis was called alpha, and that also changes. But I don't think I'm going to use that change, so I won't even write it. And the other important one which you can read off immediately from here is that there was some rule for the masses of these two Higgses, square and add it. Okay. First of all, this I think is squared on the left now. That's pretty obvious. Okay. So if I add these two, I just drop this orbital square root, and I also drop the half, and that's the answer. So this is actually the most simple and useful formula, which is sort of the rationale for all this effort we went to. The earlier sum rule said that the lighter and heavier of these two neutral Higgs adds up to the mass of the A Higgs and the Z boson squared. But now that's violated by an extra piece proportional to this 120 GeV object epsilon h, and depending on sin beta. And this is a consequence of the one loop effective potential correction under the assumption of no left-right stop mixing. Okay. Now if we take the decoupling limit, which is MA goes to infinity, in practice MA greater than 300 GeV, then we use this formula and look at m small h. By definition, small h is the guy with the minus sign, so that this cancels that as much as possible. So it's the lighter of the two neutral Higgs. Okay, and in the limit where ma goes to infinity, the leading term here cancels the leading term here. Okay, but there's a finite difference left over, and that's what we want to capture. And we find that in that limit, it's a little bit subtle calculation from there. You find that mh tends to mz squared cos 2 beta plus epsilon h square root of the whole thing. It's a nice formula, and in this formula actually the sine square beta eventually drops out. So epsilon h appears all by itself. Okay. And by comparison, the formula without this one loop correction was just that. And in fact, this is probably, maybe it's better to write it without the square root. Okay. Assume some average value of beta so that this is a number of order 1, nothing very extreme. Then you see that mh was, in this decoupling limit, was tending to mz, which was of order of order 90 GeV square, but we have a correction of order 120 GeV square. Okay, so about equal. So this really makes it very clear that this one loop correction is not something very small, it's an important derivative correction in this. And in fact, the RHS of this equation, this quantity with this evaluation that I did earlier, as well as assume that tan beta is much greater than 1, that's really in the regime where beta is close to pi by 2. So this is like cos pi, so that's like 1. Actually cos pi is more like minus 1, and I'm a little worried. Oh, it's cos square, thank goodness. So it's 1. And so basically we are not considering that. So we add up the known value of this and the estimated value of that, and we find that the whole thing comes to 110. Okay. So there's certainly some improvement. Isn't it a bit suspicious that there's such a small change?
Epsilon's in GeV squared.
Yes.
Z squared is
Thank you. Thank you. Epsilon is 120 squared though.
G squared.
Huh? What? Epsilon?
GeV squared.
I don't know why this happens. I worked it out earlier and it came out right. Cos is being estimated to be of order 1 because we've taken tan beta very large, so beta is close to pi by 2.
It's just almost the right hand. It's technically about square root of 2 points. I mean, you have to use in the space of two very similar numbers.
Yes.
So you can write that. It's
Right. So that it gives you like a factor 1.4, right? So 1.4 times the Z mass should have been 125 rather than 110. That's the only thing that's puzzling me, but what's the usually among friends. So let's hope that that's correct. Now the important thing here is that this is not great. I better keep this way. The important thing is that this is not great because this still predicts the Higgs around 110. At the end of this lecture, I'll give you the current bounds from the particle data table, but this is not very encouraging, and this makes us feel, so this is better, there is a bound better than 3-level bound, but not good enough. Higher than the 2-loop order? Yes, one hopes so. Of course, I don't even know if they have been calculated. It's not very easy to calculate an effective potential in 2 loops. So, probably if you want to do 2 loops, you would do it some other way.
But I think correction is almost as much as the key.
It's not really. And in fact, it shouldn't be. I mean, we shouldn't expect that the 1-loop correction would be as. It's not really as much. I must have said it. What I said epsilon evaluates to was probably wrong. It might evaluate to 80 squared or something. But the point is that it's a significant deviation from the 3-level value, but it's not doubling it or anything. Okay. Okay. But you're right. I mean, one should certainly worry about what the effect of high loop corrections is. Okay. Now, the fact that this is not good enough indicates that one of our simplifying assumptions or one or many of our simplifying assumptions were wrong. Turns out the one that was most wrong, and that was almost obvious from the start, was the assumption of no left-right stop mixing. Okay, so we should restore DLT or mixing, because we see that it's potentially important, I mean, the point is that we'd like to know whether when we restore it, it raises this bound because we'd like this bound to be raised. Okay. Now, as I've told you already, that means that we take the mass matrix we have and restore back terms like mt, at plus mu tan theta, and this is at star, and this is at plus mu star tan theta. So that's one change we do, but we also allow the soft breaking term for the left stop to be different and independent from the soft breaking term for the right stop. Might as well. Okay. And at the end of this, we find the following interesting conclusions. I'm not going to go through them in any detail. One is that this time H1, the imaginary mass matrix, imaginary H1 0, imaginary H2 0 mass matrix does suffer a change. Earlier, if you remember, this one didn't get a change, and only the real H1 0, real H2 0 mass matrix got changed. This time, the imaginary guy also gets modified. And the modification is rather simple. Instead of writing that, let me just give you the answer right away. Well, no, I should give you the modification. So it is m squared of imaginary H01, imaginary H10, H20 is equal to P mu. If you remember what it was before, it was P mu into tan B. It was a very simple mass matrix. Do you remember this? And the nice thing about this was it's obvious that this determinant is 0. So one of the eigenvalues is a goldstone, that's the neutral goldstone. The other is what we call A. Alright? Well, now what happens is that the change is by a quantity delta that's rather complicated, but just sits in front. It could hardly have been right otherwise, because this still better have a determinant 0, because we still have to get a goldstone out of this. No matter how many loop corrections we add, there better be a goldstone in this theory for there to be a Z boson. So the correction is outside, and with that, I just have to tell you what delta is. It's defined in terms of all the relevant quantities, which are the soft breaking masses mt left and mt right square, as well as these quantities A and mu, which disappear in the limit of no left right stopping. So it is, to be precise, minus 3 ft squared over 32 pi squared mu 8 straight up, sorry, 1 mt1. This looks a bit dangerous because it looks like this is going to 0 when we take the T1 and T2 are the top eigenstates after we diagonalize our, sorry, what are T1 and T2? 1 and 2. They are the eigenstates after we diagonalize the mass matrix. Or for the stop masses, that's right. Okay. And of course that those two would be equal in the limit when there is no mixing, as well as these two parameters are equal. Okay. But there is something I haven't yet written which has got logs in it. So it's twice mt tilde 1 square log get these brackets wrong. I've got them wrong all over in my notes. So you see that you have an expression which vanishes, this box bracket vanishes when T tilde 1 and T tilde 2 become degenerate. This also vanishes, but the ratio is finite. However, because if mu and AT were both 0, that's when we would have no mixing. and then this correction has to go to 0, so it agrees with that restriction. Right? Okay. Now what do we hope to get out of all this? Well, we take this thing and we diagonalize it, and what we are going to get out is the mass of which Higgs? A. Thank you. So we find that MA square is corrected by delta, and if you look up your notes, you will see that earlier it was the same expression as this with delta equals 0. Okay, so here we plot precisely the correction to the mass of the pseudoscalar Higgs A under the assumption that there is left-right stop mixing, and dependent on delta, which is directly proportional to both mu and AT, which are parameters that you need in order to have this mixing, as well as the independent masses of the eigenstates of the two stops after diagonalizing the left and right stops. Okay, so that's one fact. So MA changes. After that, there are only a few more formulas, so you'll have to bear with me, but it certainly is a little complicated and tedious. The last thing we need is the neutral Higgs, so we need the mass matrix of real H10, real H20. This is the thing we want most, because remember, among these when we diagonalize, we get the small h and capital H, and it's small h that we are always after. Okay. Small h is some sort of, finally is going to be something like a standard model Higgs in many scenarios or many limits of the supersymmetric scenario. So this is always what we are after most seriously. And I need to define for you 3 corrections before I can express this. Matrix. A bit tedious, but it's the last formula we'll be writing. So let's first write this matrix as delta 1 1, delta 1 2, delta 1 2, delta 2 2, where so it's all using expressions much like that, but the combinations are different. The prefactor is 3GF mt to the 4th over 2 root 2 pi squared sine squared meter, and that's common for all of these. Then it multiplies mu into AT plus mu cot theta over mt tilde 1 squared minus mt tilde 2 squared, the whole squared, and then there is some kind of logarithmic term 2 minus d tilde 1 and d tilde 2 plus over minus combination log . I've only managed to write delta 1 1, and let me not write delta 1 2 and delta 2 2. They are pretty similar. It's not very illuminating, but they are very directly calculable, and this gives you the idea of what parameters they depend on. As usual, the eigenstates of the stop masses and A and B, as well as beta, and everything else is known. For example, GF and mass of the top are all experimentally fixed. Okay. Now, in terms of these, we find a bound on the small h Higgs, which at tree level was mz squared cos squared 2 beta. Okay, and I should just say that delta 2 2 has an ingredient in it, has a term in it, which doesn't vanish even in the absence of T left T right mixing. You remember that without T left T right mixing, the only term was delta 2 2. Okay, so this goes to 0, this goes to 0, this goes to 0 when all these mu and a's go to 0. But delta 2 then becomes that epsilon h over sine square beta. Okay. So the limit here changes to this plus delta 1 cos square beta plus delta 1 2 sine 2 beta plus delta 2 sine square beta. And so we see that this fulfills all the limits we already know. This is the tree level bound. Okay. In the absence of T left, T right mixing, these two guys are 0, and this is epsilon h over sine square beta. That kills that, and we get the epsilon h extra piece added on to this, which we've already seen. Okay. But now the question is, under reasonable assumptions for the parameters, what's the value of this entire right hand side? Okay. So what are reasonable assumptions? I guess we need to figure out, we need to assume something for A, something for mu. Beta, of course, we can always take conveniently to get a bound, because anyway this is going to be, we can take beta to be pi by 2 in many cases or close to that. And then this difference, which threatens to make the expression diverge, but then there's this, but it probably still diverges. If MT1 and MT2 become coincident. But the problem is that those two depend in turn on these mu and h. So you have to do the whole thing properly. Okay. That is, when mu and a go to 0, this numerator goes to 0 with a certain power, but this difference also goes to 0. Because in the absence of top layer of T left, T right mixing, the denominator goes to 0. So, well, it's a long story, and I prefer to believe the experts. The claim is that finally this implies for reasonable values of the parameters that mh is less than 132 GeV, which as far as I can find out, still today remains the upper bound for the lightest Higgs in the MSSM. And so if the lightest Higgs is not found satisfying this bound, then MSSM is dead, but of course there are lots of MSSMs next to minimal standard supersymmetric standard models where you can get around this. Still, it would be progress to know whether this bound is alive or not. Now, for comparison, I'd like to give you what I got from the particle data table about the entire Higgs story. I am, again, not being an expert, it's very hard to decipher some of the statements they make. But this is how they describe the Higgs masses. So the first bound they give is on the standard model Higgs. And the standard model Higgs satisfies that M of capital H, this I'll put Sm here. So this Higgs is a single neutral Higgs and it is called capital H, and this is supposed to be greater than 115 GeV. Okay. The second thing they give you is the bounds on MSSM Higgs. And here you should get bounds on all the 5 different MSSM Higgs. But for some reason I could find 4, and maybe this is supposed to play the role of the 5th one, which I find very confusing. But it says that small h is greater than 90 GeV and A is greater than also 90.4 GeV. Here they say if tan beta is greater than 0.4 and the charged ones are greater than 80 GeV. Now it could be that these are somewhat old bounds, but this is still the current value of the particle data table. And if you compare these are experimental lower bounds from the fact that it hasn't been found. Here's the theoretical upper bound in the MSSM. So we see what range we are in. But as I said, I mean, these are experimental upper bounds, but since we believe that this H, at least for large regions of parameter space, behaves like the standard model Higgs, it would be more reasonable to assume that this H simultaneously has this as its lower bound, so it's bounded in a much more narrow window. Okay. I think what happens probably to get these very generous lower bounds, you we probably need to make certain assumptions about tan beta and so on, which are probably put it far away from the decoupling limit. Remember, MA being around this value is certainly nowhere near the decoupling limit. The decoupling limit is when MA starts to be 300 GeV. So if we take MA and rank it up much above its experimental lower bound, then we probably would see the lightest of the Higgs going above 115 GeV, because that's the limit in which the standard model bound applies. Okay. So in that limit, the range is above 115 and below 130. But again, we don't know that we're in that limit. And all this is pretty much near the edge of my, very dangerously close to the edge of my knowledge of this subject. But I think we've covered all the theoretical issues. Now it's only a matter of you getting down there and reading all these data and interpreting what they say. The particle data group has a huge, nice website, pdg or something.gov, which has tables of every particle, mass and bounds. But also a nice, the last link there is some kind of 40 or 50 page article on each of these different particles. So for example, if you just want to know about status of Higgs, there's like a 50-page article on status of Higgs, which has not just these numbers, but also the details which explain what these numbers mean, what are the assumptions which lead to these numbers and so on. So I strongly recommend reading that. Now, that's the end of this lecture, but also somewhat to my surprise, that's really all that I can say at this level about the MSSM. And so I would say it concludes the MSSM module of this extended course called LHC for string theorists. And I'm not going to give any more lectures till the end of this year. So this is the end of the course, the end of this part of the course. Now next, various people, it depends a lot on enthusiasm of other faculty members, notably Sandeep and Shiraz, who were enthusiastic to keep this thing going for the whole year or even longer, by having other lectures and study groups and discussion groups. And the topics then would be, one would be high scale physics, which would not directly connect to LHC per se, but would give us a better idea where these soft breaking parameters come from. That's the kind of stuff theorists love to do anyway. It will be the things that you all will find easiest to understand, I think, at least those of you who are in the string world. But then there's another extreme end that Shiraz wanted to study, which is really what data from LHC will tell us these kind of things. How can we learn to reconstruct these answers from data? And then the other thing is that there are scenarios where supersymmetry is not required or is not the only thing. For example, brain world scenarios where warping is a solution to the hierarchy problem. And so brain world, which definitely requires extra dimensions, is a whole other scenario that LHC is searching for. And so we'll be talking about that also in the next semester when this thing starts. So that's it. So thank you for coming.